each parameters. But for this one, we could just simply just make these equations have the relationship between the diameters, I mean the square of diameters of what we got, when we machine the spore size and the input pulse energy. Okay, so we just, in this case, we just try to find the relationship. We just use different powers to machine different times and get the measurement the spore size of each lines. So as you could see in here, in this case, I use 2.5 watts to 4.5 watts. So I just increase like 0.2 watts each time. So I just increase. I just draw like 11 lines for this one. So to measurement the spore size, I just want to get separate spores. That means I need to use very high scan speed to get the spore size. So as you could see in here, once I use a quite low scan speed, you will have some overlap from of each spores. But to calculate ability threshold, I want to measurement the radius of each spores. So I want the scan speed high enough to get separate spores. So the minimum spore size I calculate. So according to the equations in lab 1, for this laser, the minimum spore size is like 45 micrometers. And how to calculate the minimum spore size? Because we have used is the pulse laser. So the pulse is simply like this shape, and each pulse means the one spore of each line. So to get separate spores, we want scan speed. We want a pulse for each pulse time, and the distance we scanned is longer than the diameters of these spores. So in this part, we could get the separate spores of the lines. So how to calculate it? We just simply use the diameters of the minimum spore size to divide it with the pulse duration. And for this case, we just use waveform 0, which the frequency is 25 kilohertz, sorry. And the spore size is 45 micrometers. So you could calculate the minimum spore size. Yeah, just calculate. Don't just watch me. Divided with the pulse duration. The frequency of this pulse is 25 kilohertz. So for each spore, the spore duration is like 0.4 microsecond. So so you just divide the spore diameters to that.
So you can multiply them to.
Yeah. So the scan speed, the minimum scan speed to get separate light is like 1125 millimeter per second. But the number I use is the minimum spore size. In real machine, once I use the higher input energy, the spore size may have larger than that. So for safety, I just use 1500 millimeter per second to get separate light. So why I use waveform 0 but not use waveform other waveform? That is because you could see in here, like that is because there are some limitations of these diameters. So you could reach only like the maximum scan speed like 1600 millimeter per second. But if I just use like waveform 5, the frequency of that is 500 kilohertz. So you will like 100 times than around 100 millimeter per second. So that would be a really, really high scan speed, which just lots of just above the limitations of this scaffold. Okay. So that is the reason why I just use waveform 0 or use other waveform. For this one, the parameters is 2.5, and the scan speed is 1500 millimeter per second, and the frequency, I just use waveform 0, which the frequency is 25 kilohertz. So I just scan them. Okay, it's very fast. So it takes like several seconds to machine this pattern. So this is one of the advantage to use laser to marking the samples. So now you could see in here, we just got separate spots for different. So once we just increase the power of each line, with the spore size, the spore diameters just get a little bit larger. So I will save these pictures for you. So for you, how to measure the ablation threshold? So we could use the data parameters to calculate the input pulse energy. And then we could use same software, ImageG, to measurement the spore diameters, the diameters of each spores. And then we could get a relationship of these two parameters, and then we could calculate the final results. So as you could see in here, when we use quite low energy, the ablation area is quite small, because the input energy is quite low, so it will only evaporate a little bit and materials of the sample, and the materials and the material just evaporate, and then it becomes solid very quickly. So it just becomes this melting area. So you could see in here, once we just increase the power higher and higher, the spore size, the spore diameter just get increased, and we could get very deep spores of each line. Okay. So this is how we just calculate, how we measurement and calculate the ablation threshold. So in this part, do you have any questions of that? Okay, so I will clear. But you could see in here, this laser system can control a lot of parameters, like power, laser power, and the scan speed, and the different waveform. So we need to find to minimize the range of each parameters. So for the first one, for the first experiment, we need to find the relationship between the waveform and the scan power. So we just made the scan speed constant into 100 millimeters per second, and changed this one, and changed each one from waveform 0, each line from waveform 0 to waveform 5. So can anyone help me to change the other parameters? So first we just change this test from into waveform 1, waveform 2, waveform 3, to waveform 4.
All this. One.
This one. Click this one. And click test 2D. Just type waveform 1.
Apply.
So we need to change the parameters of each one. So click this one and double click. Yeah. So this one we just power is 16, and the scan speed we just made it constant into 100 millimeter per second. 100. And we just use waveform 0. So the frequency we could see in here. So for the waveform 0. The frequency is 25 kilohertz, and we need to also change into here as PIX3 into waveform 0 here, and click OK. Okay. Double click in this one. So it's same thing. Yeah. So change into waveform 1.
65. Yeah, waveform 1. One, two, five.
The power is 16.
16.
Power. So once we change the power, we could start machine that one.
Excuse me, sorry. The power, is she going to change the power for all of them, the waveforms?
Sorry? All of them is 16.
That's
so
okay.
we could just machine these squares in one time. So first we just machine the tests or the sample. Sorry. So first I just find the positions I want to machine. So we could start to machine the tests of this one. Okay, so I just select all of these tasks and click mark, star mark. Okay. And this one. So because we just already changed the parameters of this one, so we could just select all of them and click once. So you could see here, because the energy is really high, so there's lots of materials become plasma, so you could see very shiny stuff in the surface of these materials. So anyone else could help me to finish these samples.
Okay, cool.
You not automate this usually.
So we just change this into chop loss. others you don't need to change. So just select this square and click mark. Okay, start mark, start point and start mark. So you can see here, not finished. So just change into 8. So you can see here is for the first square, it has really shining bar. That means the input, because we just use waveform 0. For waveform 0, you have a lossless frequency. So for as you can see in here, because like what we have used is power. So for 1 second, we will input the constant energies for the sports. But for higher frequency, they will have more pulses in that 1 second, but the energy is constant. So for higher for the higher frequencies, the average pulse energy is lower. So for waveform 0, you will have highest pulse energy, and for waveform 5, you will have lowest pulse energy. So that's one of the reasons why we machine the first square, you will get the sparks, the most shining